So we have to understand a little bit about light before we can talk about electrons. And so we'll take a little foray into physics here. We need to understand light because it was the interaction of light with atoms that helped scientists to understand and develop the models for the atoms. Light is a form of electromagnetic radiation. So it involves electric and magnetic fields. It's a type of energy. Light is energy. And it travels through the space at a constant speed. We call it the speed of light. It's 186,000 miles per second. That's a lot. 186,000 miles in a second. Of course, we're in chemistry class, so we have to put that in the metric system. It's 3 times 10 to the 8th meters per second. And what's really interesting about light is it has properties of both waves and particles. So if we look at water and we disturb the surface of the water, we see waves, right? We see waves created. Here's water dropping onto a still surface, and the waves travel out. The waves are carrying energy. If you've ever been to the coast and stood in the surf and had a big wave hit you, you understand that there's energy in a wave, right? It can knock you flat. There's a lot of energy in that wave. Now, ocean waves don't travel in perfect sine waves like this, but light does. It does look a little bit like waves, though, on the ocean or on a lake. So waves have a few characteristics. One of them is wavelength, and the wavelength is the distance between adjacent crests or peaks of the wave. It's the length of one wave. So if the wave starts up here and goes all the way to the bottom and comes back up, that's the wavelength. And that's given the symbol lambda. It's a Greek letter lambda. It's like an upside down Y. For visible light, this distance is what determines the color of the light. If the color is, if the wavelength is a little longer or a little shorter, the color that we observe is different. So we have this wave and it's traveling along in this direction. So if you were a bystander standing right here, what you'd see is this thing going up and down as it travels past you. And we call this a crest and this a trough. White light, which is what comes off of light bulbs in the sun, contains a whole range of wavelengths. And if we take an incandescent light bulb or light from the sun and pass it through a prism, we see a rainbow, don't we? And it's beautiful, and we like rainbows, and they're pretty. And if you go out in the summer and the sprinklers are on and you stand in just the right place, you can see little rainbows in the sprinklers even, because the water droplets act as prisms. Well, why does light do this? Did you ever wonder about that? Why does light do that? The prism is separating the light according to its wavelength. And so here's the red light. It has one wavelength. There's yellow, and there's blue, and there's purple, and they all have different wavelengths. And when they pass through a prism or a droplet of water, which acts like a prism, or the light fixture that hangs in front of my door, and every afternoon it spreads little tiny rainbows all over the walls, and the kids think it's really cool. The light bends in that glass or the prism or the water droplet differently depending on its wavelength. Why do things appear to have different colors? It has to do with the light that is reflected. So here we see a woman standing in the surf, and she's wearing a red shirt. Why does her shirt look red? Because her shirt is absorbing all the colors except red, and it is reflecting the red. And so we see the red light coming off of her shirt. So we look around the room, and we see different colors, right? I see a red water bottle. It is absorbing the other wavelengths of light and reflecting red. A pink shirt. My green binder. It's reflecting the green light. Black things absorb almost all of the light, and white things reflect almost all of the light. That's why if you're outside in the summer here in the valley where the sun is just brutal, do you want to be wearing a black shirt, standing in the sun? No. It's going to be hot because it absorbs that energy from the light. A white shirt is going to be much cooler because it's going to reflect a lot of that energy. Another idea about light and its waves is frequency. And this is the Greek letter nu, which looks a lot like a V, but it's got a little curve on it. And so it's not V. V is for velocity, nu is for frequency. And I'm sorry they're so similar. Can't do anything about that. Frequency is the number of cycles or crests that pass through a stationary point in 1 second. I need a picture. So let's say that you're standing here. And here's the wave of light, which of course, we can't see its waveness, but. So if you're standing here and the light is traveling past you, light always travels at the same speed. So if you're counting crests that come by in 1 second, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the number of crests or troughs that pass you in 1 second, that's the frequency. The frequency is going to be related to the wavelength. Because if these waves are moving at the same speed, at the same velocity, and here we've got one with a shorter wavelength. It's kind of hard to draw. So here's the wavelength of that one. And this is the wavelength of the yellow one. Which one are you going to count more crests in a second? The blue one or the yellow one? The blue one. Is it traveling faster? No, they're both going at the same speed. It's going up and down faster. So it has a higher frequency. It's got a shorter wavelength. The yellow one looks slow, at least it looks slow to me, but they're both moving at the same rate. Okay? So if you have a long wavelength, then the frequency will be low. And that's what this means by wavelength and frequency are inversely related. If one is large, the other is small. If the frequency is high, the wavelength is small. If the frequency is small, frequency is small, the wavelength is high. I don't think I did that right. That's okay. We'll just go on. So light acts like a wave, right? Light can also be viewed as a stream of particles. This is a little harder to understand. You've probably heard the word photon, though. What do you associate photons with? Star Trek. Fire the photon torpedoes, right? Photon. Photons, actually a photon torpedo is not as crazy as you might think. A photon is a piece of light, a particle of light, or a packet of light energy. So it's a little hard to think about. It's like a piece of milk, right? How can you have a piece of milk? But a photon is a particle of light, a packet of light energy. And that the amount of energy that's carried in that packet depends on the wavelength of the light. If the wavelength is shorter, it has more energy. And if the wavelength is longer, it has less energy. So the light waves carry more energy if their crests are closer together. So again, we need a picture. So how can you remember this? So there's our long wavelength, right? Light. And here's our short wavelength light. Which one looks like it has more energy? The blue one, right? It's jumping up and down. It's like moving all over the place. The short wavelength because it's moving up and down. They're both going the same speed. It carries more energy than the one with the longer wavelength. Yeah. So we're skimming the surface of this topic, and so I'm talking about it in kind of personifying matter kind of ideas. So don't go to your second semester physics class and say, well, Mrs. K said because it's bouncing around more, it's more energetic. No, that's just a way to help you to remember. This one that's going up and down faster, it's got a higher frequency, it's got a short wavelength, and it's got more energy. So we've got energy, frequency, and wavelength, and they're all related. And it's real helpful to just have an idea of how they're related. And so that's how I remember it. I look at the one with the short wavelength, and it just looks like it's got more energy.
I thought of it like a heart monitor. Watch someone's heartbeat. They have more life than.
That's a good idea. Think of it as a heart monitor. And so here, somebody whose heart is beating faster, they've got more life than someone or more energy than someone whose heart is beating very slowly. Yeah. Good way to think about it. So here's that relationship again. Long wavelength, low frequency, low energy. Think of that big, slow. It looks slow because it's going up and down slowly. They're both going at the same speed. So that's these guys over here. This is long wavelength, but low frequency. As we go over here, the wavelength gets shorter and shorter, and the frequency gets higher, and the energy gets higher. Question? The speed stays the same. All light travels at the same speed, the speed of light, 3 times 10 to the 8th meters per second. So this is the entire electromagnetic spectrum. Okay, and the visible light is just this little tiny section in the middle. But it's interesting to us, and so we're blowing it up here. And here they're telling us what the wavelength is. And the wavelengths here are expressed in nanometers, or 10 to the minus 9 meters. So the red light has a longer wavelength, and the violet light has a shorter wavelength. Which one has more energy? The short wavelength. So when I answer a question like that, I actually do this little process of thinking. I think, okay, short wavelength, and I imagine that wave. Oh, that one's energetic. Okay, so that one's more energy. So what's next in the most, as we go to increasing energy, the next type of radiation is ultraviolet radiation. That's what gives you a sunburn. Is there energy in that? Yeah, there's energy in that can burn your skin. All of this contains energy, but the red light is lower in energy than the violet light. Yes?
I have 2 questions.
Mm-hmm.
So then since there's more energy, in purple, then is that why like a hotter flame is blue because there's more energy then? Or
That's a good question. The question is the hotter Bunsen burner flame being blue as opposed to yellow, is that correlated to the wavelength of the light being given off? I think that it probably is. We're going to learn later in this chapter why light is given off from something like that. But I think you're probably right. You said you had 2 questions.
Yeah, and then my other one, so like how you say the reason this is yellow is because yellow light's reflecting.
Mm-hmm.
So does that mean that in everything, literally there's something that's, I don't know, like their atoms or particles or something are different that they make things bounce off?
Yes.
So when you have like red dye, blue dye, green dye, there's actually something in each of them.
Right. Things are different colors. Like you think about like paint or dyes in food. Why is green Kool-Aid green and red Kool-Aid's red? Well, there are dyes in there. The red dye is red dye number 40, which my son's allergic to. But Dyes, which are used in food coloring, and they're also used in clothing, are molecules that interact with light. And so they will absorb particular frequencies of light. The frequencies that they don't absorb, they reflect, and that's what color we see. And most dyes are rather large organic molecules that absorb light. And some of them, if you just change a little bit about them, they'll absorb differently. And that's where you get the color-changing spoons. And it used to be a big deal. We had these T-shirts, and you went out in the sunshine, and the colors would show up, and you went back inside, and the colors would disappear, and it looked like a black and white T-shirt. And that's a molecule changing in response to a stimulus, and because of that change, it absorbs light differently. Yeah, it's really, really interesting.
So the same thing with yellow and blue makes green?
Yellow and blue makes green. And so, yeah, that's a whole nother interesting subject of mixing different colors together and the things that you come out with. And it's really physics is what it is.
For long wavelength, does it go further out? Or?
Does long wavelength travel farther? Yes, actually it does.
Red stop sign, right? Like you can see it from far away, or the red light at a full stop.
See.
Sure, you can see it from further at night. Maybe.
I know that our eyes are more sensitive to certain colors than others. I don't think that the distance traveled by red light as opposed to violet light is significant. I think it's a situation, they chose red for stop signs because there probably is there's not a lot of red things in the environment. You don't want a green stop sign because there's trees all over the place, right? You don't want a blue stop sign because it's going to fade into the sky. And you don't want gray. And so certain colors just pop out at us more. There's that particular color of neon yellow greenish color, right? And it'd be really interesting to study how do they get it. I mean, it almost glows, right? I keep buying shirts for Andrew in that color because then, like at the baseball game, I can find him, right? Because I'm like, oh, there he is, because he's always just wandering about. But in terms of traveling farther, over here we get into radio waves, and radio waves. The lower energy, longer frequency radio waves travel farther. There are some AM radio stations. I remember growing up in Minnesota, on particular evenings, I could pick up AM radio stations from Texas because, the conditions were right that the waves were able to travel, and they'll go long, long distances. And you see a similar effect with sound waves, which are different than light energy. But what sounds do you hear from that loud car? You hear the bass, right? And the marching band that's practicing in the next neighborhood. You hear the bass more because those long waves are able to go around obstructions better than the small ones. They just travel farther. And again, that's physics. Physics is pretty interesting too. The thing about physics, though, is the first year of physics is awesome. Then after that, it gets really, really crazy. So that's why I didn't go into physics. Not that chemistry isn't crazy, right? Let's see, is this a new section? I don't know. So let's talk about these. So on this thing, I'm sorry, I'm flipping back and forth. Here we got radio waves, and these have these. This is all in wavelengths, in meters. So radio waves have wavelengths like 10 meters long, 1,000 meters long, a kilometer. A wavelength that's a kilometer long. That's really long. And then as the wavelength gets shorter, we've got microwaves. And yes, those are the microwaves being generated in your microwave to heat your water or your green beans or whatever. Then we've got infrared radiation. Ultraviolet is more energetic than visible light, X-rays and gamma rays. And we're just going to talk real briefly about these. Start with the most energetic. Gamma rays have the shortest wavelength of the electromagnetic spectrum. They are the most energetic. Gamma rays are produced by the sun and the stars. There's a lot of nuclear reactions going on in there, and they're also produced by certain unstable atomic nuclei on Earth. Okay, and so that is, because when we think of electromagnetic radiation, right? Radiation, bad, right? Protect yourself, right? Well, radiation can be good too. It just means something that radiates. But gamma rays are the dangerous, very dangerous kind of radiation given off by nuclear reactions. Then there's X-rays. X-rays are able to pass through many solid substances, and they have less energy than gamma rays, but they're able to pass through many things. Both gamma rays and X-rays have medical uses. They can be used for destroying tumors. They are energetic enough to damage biological molecules. So that's how you can use it to destroy a tumor. They're good for imaging. Too much is very, very bad for you and will definitely kill you. So how do you use a dangerous, high-energy radiation to kill a cancerous tumor without killing the person? That's the problem with a lot of cancer treatments. It's like, well, yeah, we could kill the tumor, but the problem is killing the tumor without killing the person. So when they use radiation, what they'll do is they'll take radiation beams from multiple directions, and each of these is weak enough that it can pass through the healthy tissue while causing an acceptable level of damage. It does damage the healthy tissue, but just a little bit, and it's considered to be acceptable. You know, you've got a cost-benefit ratio. But they're all focused on the tumor, so you're hitting the tumor from different directions, and so the tumor ends up getting all of it together, and so they can destroy the tumor that way.
So now the new study about cancer treatment, they're talking about shooting like a beam at it now.
Mm-hmm.
Instead of going all around it like that. The new research is saying that they're shooting, she described it as taking a like sniper to it instead of just throwing a bomb on it.
Interesting.
That's the new research.
So there's a
That's kind of
new
the idea.
technique that's different than this, where they're just going one shot, high energy, and you probably are also damaging the healthy tissue along the path, but if it's small enough, maybe it doesn't matter.
Yeah, I guess that's the whole.
Yeah, I haven't read about that, but
It makes sense looking at the picture.
right. So, you know, when you do radiation this way, you're going to get damage in all these different directions, but you're going to get a lot more damage on the tumor. You know, because if you have cancer and you do nothing, you're going to die, right? So if you do radiation treatment and the radiation damages some of your healthy tissue, well, that's not good, but if you did nothing, you were going to die, right? So you have to weigh the benefit and the there's another word I can't.
The quality of life.
Well, quality of life, I'm thinking, you know,
Quality of life and also
cost, it's not cost,
it
but,
only sometimes prolongs.
right.
It's only a difference of a year or two, and
Right.
during that time, what is your quality of life during that treatment?
Right, and that's why, you know, like with chemotherapy makes most people very, very ill and miserable. I personally think that being nauseous is the worst thing ever. I'd rather have straight pain than being nauseous. And so, you know, if it's going to cure you, if the chemo's going to cure you, then fine. But if it's just going to prolong your life, maybe it'd be better to feel good for a shorter amount of time than feeling awful for longer. And those are the really, really hard decisions that have to be made. Next down in the energy level is ultraviolet or UV light. UV stands for ultraviolet. This is the part of sunlight that causes a sunburn. Less energetic than X-rays, but obviously still damaging to biological molecules. I've had plenty of sunburns in my day. Next is visible light. Visible light does not damage biological molecules. The idea of vision if you've never really thought about this, how do we see, right? What is vision? I mean, if you stop and think about things too long, you can really kind of freak yourself out. How do we interpret this light waves around and allow us to see what's going on across the room, right? Well, the light hitting your eye causes molecules in your eye to rearrange, and that sends a signal to your brain, which your brain has learned to interpret. It's really pretty interesting when you get into that, that's not chemistry, so we're not going to get into it. Next is infrared light. So, when I was growing up, we'd go on family vacations and we'd stay in hotels. And one of the funny things about hotels is they always had these heat lamps in the bathroom, right? And it had a timer and you turn it on. There's this light in the ceiling and it kind of had this reddish glow, but it didn't give off much light. But it gave off a lot of heat. And it's like, oh, wow, that's really neat, right? Infrared light. Infrared, it's below red in terms of energy. And that's heat. And so when you have a warm object, like when we did the crucibles, I warned you, put your hand near it. And if you feel heat, don't touch it, right? What's that heat coming off of it? There's actually infrared light, which our eyes can't see, that is being given off. And this is the basis for night vision devices. They can pick up, you can make electronic sensors that can pick up the infrared light. So anything that's generating heat is going to give off infrared light. I think we got a picture. Yeah, here's a picture. So here's a guy and his dogs. And looks like this poor guy has some sort of an issue. He's got a cone, one of those cones on his head. And here, this is taken at a slightly different time because now the dogs are facing you. But this is an infrared photograph. So this is using infrared light. This is using visible light. And what we see is very different. We see that the dog's ears and eyes are warm, and we see that the dog's nose is cold, right? And here, the guy is wearing shorts. And so where his skin is exposed, we're getting more infrared energy off, and here his shirt and his hair are sort of insulating from the heat. So this is the sort of thing that you'll see with the infrared night vision. And it can be really helpful for, like, trying to find somebody who's hiding in the woods, right? Because you can fly your helicopter over and you can't see them, maybe even with a searchlight. But it's hard to hide that infrared light. Microwaves. Microwaves are used for radar and in your microwave oven. And the microwave oven works because water absorbs electromagnetic radiation in this frequency wavelength region very efficiently. And so it's the water molecules in your food that are absorbing the energy and getting hot. And then there's radio waves, and these are used to transmit AM, FM radio. Your cell phone signal is a radio wave, television, all kinds of other forms of communication. So when, on the radio, when you have, it's 99.1 or whatever the number is, that's actually the frequency of the radio station. And so you tune your radio to a different frequency and you get a different station. Question? So arrange the three types of electromagnetic radiation: visible light, X-rays, and microwaves. So we're just looking at three of them in order of increasing wavelength, frequency, and energy per photon. Okay, so this is a little challenging to do from memory, not having studied this at all. But let's just think about that spectrum that we looked at. Okay, so visible light was in the middle. So visible light. And this was higher energy over here and lower energy. Sorry, didn't run it right up there. Lower energy over here. Were the X-rays more or less energetic than visible? More, right? They were over here. So the X-rays are over here. The microwaves, which side of visible were they on? They were on the less, right? So micro. Okay, so if we kind of do this picture, and this is what I would do in my head if I was answering this question. I would imagine that spectrum. So in terms of wavelength, how did the wavelength change? Which end of this guy was long wavelength? This is long over here, and this is short, right? So short wavelength, and this is high wavelength. So in terms of wavelength, increasing wavelength, that's going from short to long. So it would be X-ray, visible, microwave, right? So X-ray to visible to microwave. So the microwave has greater wavelength, longer wavelength than visible, which is longer than X-ray. How about frequency? The frequency is going to go in the opposite direction because a short wavelength has a high frequency. It's going to go past you. You're going to see more peaks in a second. So to do frequency, we just flip this around. The microwaves are the lower frequency, and the visible's in the middle, and the X-rays are higher frequency. How about energy per photon? So don't let the per photon mess you up. Energy. Which one's higher energy? The microwaves. So this is going to be the same as the wavelength. So X-ray. No, I'm sorry. It's not. It's the same as the frequency. The microwaves are the lower energy. And then the visible. And then the X-rays are highest energy. Any questions?